So today we're going to look at more rules for taking the derivative. We're going to look at the chain rule, but before we get into the chain rule, let's just quickly review what a composition of two functions is. We're going to be using that fact when we're using this chain rule to take the derivative. And so when we're looking at composition of two functions, f of x and g of x, there's a couple ways that we can write this. This we would say f with a little circle in between g, and in parentheses around that f circle g, and then parentheses x. So this reads f of g of x. The notation I think makes more sense of what we're doing is f with a parentheses, then g parentheses x. And so basically all you're doing in here is you're plugging in the function g of x. Wherever you see an x and f of x. So for instance, maybe we have g of x is equal to x plus h. And let's say that f of x is equal to x to the fifth minus 2x plus 1. And if I wanted to look at f of g of x, I'm going in here and I'm plugging in my equation g of x wherever I see an x and f of x. So just like we were looking at when we were taking the limits of the difference quotient, the formal definition of derivative, we had to plug in that x plus h wherever we see an x. And so same kind of idea here. Wherever we see an x, let's put a parentheses big enough to plug in x plus h. So we have a parentheses raised to the fifth minus 2. I see an x, so parentheses plus 1. So going in here, we have the composition there of f of g of x. What if it went backwards though, and it says find g of f of x? So instead, and sometimes it's helpful, we could go in here if we want to, and we could rewrite what our equation f of x is. So we're going to be looking at g of the equation of f of x is this x squared minus, or x to the fifth minus 2x plus 1. And this time we're going to go into the equation g of x, and wherever we see an x in this g of x, we're going to put a parentheses and we're going to go back in and plug in f of x. So putting a parentheses here because I see an x big enough so I can plug that all in, plus an h. So this would be x to the fifth minus 2x plus 1 in parentheses and then plus that h. I technically don't need that parentheses there. I could drop that. And I notice back up at this f of g of x, I probably could distribute that -2 if I wanted to. But I just wanted you guys to get the idea of this composition of functions and what we're doing. And so notice it's very important to notice that there's a difference between f of g of x and g of f of x. And normally they are not the same thing. When they are, then it's usually that they're inverse functions of one another. But we don't need to get into that. So it's actually helpful to go backwards. So given a function, can you figure out what is this inner function? What is a function I can think of that I'm plugging in everywhere that I see an x in this outer function? So how about I have some h of x function. This is equal to the square root of 2x plus 5. And so the function, the inner function, if I'm looking at this, I changed the colors, might help you, is going to be what's underneath the radical. So let's call this some function, maybe g of x. So let g of x equal this 2x plus 5. And we're trying to, in this example, find f of x and g of x such that h of x is equal to the composition of the two, where g of x is the inner function and f of x is the outer function. So think about what f of x would have to be if this was my g of x function. So I'd have to think, okay, wherever I saw an x in my f of x function, I want to be able to plug in g of x and get this whole thing back to have that h of x. So just looking at this, I can tell that f of x would have to equal just the square root of x. And so I can see, and we can show it, that h of x is equal to f of g of x, which if we go back in and plug this in, or maybe we can rewrite it as this is the same thing as f of the equation of g of x, which is 2x plus 5, which is equal to the square root. Wherever we see an x, we're going to plug in that 2x plus 5. So any questions on that so far?
How did you get f of x in the last one? Or was that just something?
No, so that was something I had to come up with. I had to figure out if I chose my g of x function to be what was underneath this radical here, I had to think to myself, okay, I need some function f of x so that when I go back in here and plug in g of x, I want to get back this whole equation. And so basically what you do is you look at your original equation, you figure out what your inner function is going to be, and wherever you see that inner function in our original, you're going to replace that with just an x. And so I knew that I needed a square root, and then I needed just the x so that when I plug in g of x underneath that radical, I would get the same thing. Does that make sense?
Yeah.
Sometimes there's, multiple different ways that we can write composition of functions. I could have chosen a different g of x for this example here. And if I had chosen a different g of x, then how I would have written f of x would have been different. I just want to show you this, but this is not how I would have done it if I was going to be breaking this down to use the rule I'm going to give you, the chain rule. But for instance, let's say that, again, we have this h of x. And this is equal to the square root of 2x plus 5. And instead, maybe I decided to choose my g of x function, my inner function, to be 2x. So if that was the case, and I needed to find some f of x function, we want to find some f of x such that when we look at f of g of x, this is equal to h of x. So we want to go back to our original function g of x. We want to see, h of x. We want to see where g of x is in this function, which is right here. So when I figure out what f of x is, I'm just going to put in an x wherever I see my g of x function. So in this case, this would equal the square root. I see a 2x here, so I'm going to put in x. And then I'm going to put a plus 5. So now, if I tried it out and I looked at f of g of x, this would look at like f of plugging in 2x. That's what g of x is. Parentheses. So going into our f of x function, and wherever we see an x, we're going to replace it with 2x. We have the square root. I see an x there. So I'm going to replace that with 2x plus 5. And this is what our original function h of x is. So I was just showing that we found something correct, that if we took the composition of f of g of x, we got back h of x. So notice there's, multiple ways that we could write this. So let's look at maybe a couple more. So usually when we're using this chain rule, it's because we have functions within functions. And we could even have functions within functions within functions. And this is kind of the reason why they call it the chain rule. We keep on taking derivatives, and you'll see that in a minute. So let's look at one more. Let's say h of x, or a couple more, is equal to, I don't know, 7x squared minus 2x plus 1. And this is raised to the 100th power. So right now, we don't know how to take the derivative of that without expanding out 7x squared minus 2x plus 1 and writing that parentheses out 100 times. And then we could go through and take product rules and multiple times, or just distribute that out 100 times. It would just be so tedious, right? And so we want to be able to manipulate this to make it easy for us to be able to take this derivative. And this is, again, where the chain rule is going to be coming in too. So we want to find two functions. F of x and g of x, such that h of x is equal to the composition. And you have to decide which one's going to be your outer function and which one's going to be your inner function. And I'm just going to say g of x is my inner function here and f of x is my outer. So we're going to go in and we're going to choose what we're going to let g of x be. Usually you want it to be everything that's either underneath a radical, everything that's inside a parentheses that's raised to a high power. Another good tool is if it's something in the denominator, maybe choose the whole denominator as your inner function. So let's choose g of x to be what's inside that parentheses there, this 7x squared minus 2x plus 1. And then our f of x function, this has to be the outer function, so that wherever we see this g of x in our h of x function, we're going to replace that with an x. And then write everything else the same as this function. And so this would be x to the 100th power. So I can see right away, if I go in and wherever I see an x in here and I replace it with this g of x, I get back h of x. So we found both our inner function and our outer function.
Professor, how did you get the x for f of x? That's, I think, where I'm getting kind of lost.
You have to decide, because this outer function, you have to decide, okay, I needed this to be the same thing as this function when I take the composition. And so you're gonna, for the outer function, you're gonna put an x wherever you see the value that you had chosen to be g of x. And so this is g of x here. So I'm gonna, when I write f of x, I'm gonna just put an x here. And then I'm going to keep everything else the same, which is this to the 100th power.
So you can just choose anything to make it g of x?
Basically, but usually what you, to help us when we're doing this derivative, we're going to want to choose it to be usually something that's inside a parentheses, or something maybe that's repeating itself.
Okay.
So if you had, let's say, let's look at another example. If you had h of x is equal to 1 over x squared minus 9. We, right here, if we wanted to rewrite it, so find f of x and g of x, I'm going to do st as such that h of x equals that composition, f of g of x. So in this case, usually I don't see any big parentheses or so no radical, but in this case, I could choose my g of x, and this is what I would probably do, is the whole denominator. So if g of x was equal to this x squared minus 9, my f of x function, all I would do is go back, look at my h of x, and wherever I saw this x squared minus 9, I'm going to rewrite that with just an x. And I have to write everything else the same. So I have a 1 in the numerator. This is all over, but now I'm seeing this x squared minus 9, my g of x function. So I'm going to replace this with x. So if I go in and I plug in x squared minus 9, wherever I see an x in this function, notice I get back my h of x. And so we found the two functions that would work for that composition. Okay, so the chain rule, and there's a couple different ways that we can write this and kind of approach it, and I'm going to do it both ways. To me, I think the easiest way is using the following notation. Okay, so let's say that if y is equal to f of some function g of x, so a composition of two functions, then the derivative of y, dy dx, is equal to f prime of g of x all times g prime of x. So let me kind of state this in words. So this f prime, this is the derivative of the outer function but it's a derivative of the outer function with the inner function in there of the inner function. And then it's times the derivative of this inner function. Okay, so there's our chain rule. And again, we'll look at an example and I'll explain again why we want this rule. Sometimes we couldn't even differentiate without that rule, but sometimes, a lot of times, this rule makes our life so much easier. Okay, so this chain rule shows us why we needed to figure out how can we rewrite a function that we're given to take the derivative as a composition of two functions. So that was a whole point of that kind of quick review of composition of functions. And we're kind of looking at it backwards than what we were looking at it when we were in algebra. So let's look at an example. We're given that, let's say, y is equal to 6x squared minus 2x plus 1. And this is all raised to the 50th power. So this is a case where we do not want to have to expand out that parentheses and multiply that trinomial 50 times, and then use our general power rule. So we're going to go through here and we're going to figure out, let's find the outer function and the inner function. So my outer function, I can, if you want to do it backwards, would be this. So some x raised to the 50th power. My inner function would have to be this polynomial on the inside, which is this 6x squared minus 2x plus 1. So going backwards, I chose what was inside to be my g of x. When I looked at my original function, I looked at where my g of x was, and I replaced this with what x was and wrote everything else the same. Okay, so that rule says I need to find the derivative of the outer function. So I want to find f prime of x. Well, that's not bad, right? All we have to use is that general power rule. So all we're going to do is bring our power down front, 50, times the x and subtract 1 from our power. So 50 minus 1 gives me 49. Now let's look at g of x. Okay, that's not bad taking the derivative. Again, all we're going to do is use our general power rule of each term and sum them. So the derivative of 6x squared, bring our 2 down, 2 times 6 is 12, x, subtract 1 from our power. So that just leaves us with a 1. Minus derivative of 2x is just 2, and the derivative of our constant is 0. So we found out what f of g of x, or what f prime of x is and what g prime of x is. So let's go back in and use this. So it wants me to look at f prime, which is this piece of g of x. So another way to write this is f prime of my whole expression I chose g of x to be, which is 6x squared minus 2x plus 1. So if I go and do that, if I go in and plug in g of x wherever I see an x in my derivative of f of x, excuse me, this is equal to, so we're going in here and plugging this in here. So this would be equal to a 50 outside. I see an x here, so put parentheses, and then raised to this 49th power. So we're going to put inside the parentheses the 6x squared minus 2x plus 1. So that was the first piece, the derivative of the outer function of the inner function. And now we need to multiply it by g prime of x, which we have right here. So putting it all together, f prime of g of x times the derivative g prime of x, well, that's equal to this f prime of g of x, which we found to be 50 parentheses 6x squared minus 2x plus 1 raised to the 49th power times our g of x, this parentheses, make sure you have parentheses around the whole thing, 12x minus 2. So a lot more easier than going through and having to multiply and expand that out first. And this is our derivative of y. So dy dx equals this. Or another way to write that is y prime equals that. So there was a great question about the answer, and can we just distribute our coefficient 50 inside the parentheses? And you got to be careful. We can't distribute that 50 inside a parentheses when that parentheses is raised to some power. And so basically, if you're looking at order of operations, please excuse my dear Aunt Sally, we'd work in parentheses first. Well, there's nothing in here that I can simplify because they're not like terms. Then we would move to exponents. So we'd have to expand this out 49 times before we went in and multiplied. And so we can't distribute a coefficient inside a parentheses that is raised to any other power than 1. But that's a common error that students tend to make. And so I just wanted to kind of come in and answer that question and state that to the whole class. Okay, so let's look at a different example. This time we're given that h of x is equal to parentheses 2x minus 3, and then that is quantity cubed. It asks us to find the derivative of h of x. We're going to try to do this in 2 separate ways. We're going to show it using the chain rule, and we're going to show it by rewriting this somehow and taking the derivative. Maybe let's go that way because let's start that way because that's what we were doing before we could use this chain rule, what we just learned. And so h of x is 2x minus 3 quantity cubed. Do not cube each term in there. That's not correct. This is saying I'm looking at 2x minus 3 times 2x minus 3 times the quantity 2x minus 3. And so we could stop here and not expand it. And if I did that, I would have to use the product rule. And I could think of the product rule of this first piece with 2 parentheses times the second parentheses. But if I did that, then I'd have to use the product rule within the product rule because this first function would have a product. So I don't want to use the product rule and the product rule within the product rules. To me, it will look easier if I just expand. So let's distribute out 2x minus 3 times 2x minus 3. So doing that real quick, 2x times 2x is 4x squared. 2x times negative 3, so that's minus 6x. Negative 3 times 2x is minus 6x. And negative 3 times negative 3 gives me plus 9. So I have that multiple times, I can't forget that third parentheses, 2x minus 3 from above. Well, before I distribute again, I would probably simplify inside my first parentheses so I don't have to distribute 4 different things. I'd only have to distribute 3 different things. I have 4x squared minus 12x plus 9, all times 2x minus 3. Taking each term in the first parentheses and multiplying it to each term in the second parentheses. So 4x squared times 2x, that's an 8x cubed. 4x squared minus times negative 3 is negative 12x squared. So now jumping to negative 12x and distributing it, negative 12x times 2x, that is a negative 24x squared. Negative 12x times negative 3, that is a positive 36x. Now jumping to the 9 and distributing it to each term in the second parentheses. So 9 times 2x, so that's plus 18x. And 9 times negative 3 is minus 27. So let's combine like terms, and then we can go ahead and take the derivative. So looking at like terms, I don't have any other cube besides this 8x cubed, so I bring it down. I have a negative 12x squared minus a 24x squared. Same sign, add them, and keep the sign the same. So this is minus 36x squared. I have like terms of 36x plus 18x, same sign, add them, keep the sign the same. So 36 plus 18, let me see, 8 plus that's 14. That's going to give me 54x. And then there's no other constants besides that negative 27. So bring down minus 27. So now we can go in and take the derivative using that general power rule. So doing that, bringing our power down front, multiplying it by the coefficient in front. So bringing down 3, multiplying it by 8, I get 24. X, subtract 1 from our power, it's now squared. Minus, bring our power down, which is a 2, multiply it by the coefficient of 36 in front, which is 72. Subtract 1 from that exponent, x. Plus the derivative of 54x, which is 54, and the derivative of negative 27 is 0. So that was one way to do it. The other way, and I did an example that wasn't too tedious, is using the chain rule. And so we need to figure out what we're going to choose our outer function to be and what we're going to let our inner function to be. So the inner function is the inside piece. So let our g of x be 2x minus 3. That means our outer function f of x is just x cubed. So just replacing this 2x minus 3 with an x for my outer function. So we needed to find the derivative of the both to apply the chain rule. So f prime of x, this is 3x squared. And g prime of x, general power rule, derivative of 2x is 2, derivative of a constant is 0. So we just get 2. So again, writing out what the chain rule is f prime of our inner function g of x times g prime of x. So f prime of our inner function, which is 2x minus 3, times my outer function, which is 2. So I have to go back in here. I need to figure out what f prime of 2x minus 3 is. So if I'm plugging in 2x minus 3, wherever I see an x here, to rewrite this, I have this 3 in front, parentheses, because I see an x. I'm going to square it, times the 2 out here. So I would probably clean this up a little bit. So h prime of x is equal to this. Notice I have a 3 in front of the parentheses and times a 2 behind that parentheses squared. So we can multiply 3 times 2. So this is equal to 3 times 2. So 6 parentheses 2x minus 3 quantity squared. So it's hard to tell, right now that these are equivalent to one another without either trying to factor one or expanding the other. But I do want to show that they're the same. So it doesn't matter to me looking at it, and it kind of can clue me in how to kind of factor this. I should have a 6 in common with all of those 3 terms that I can pull out, and then it should be able to be factored. I think it might be easier to expand. Although factoring could be a good, let's factor. And the reason why I'm going to factor is because sometimes, and we're going to get into finding when the derivative is 0. And I can't find when the derivative of h prime of x is 0 without either factoring in this case or using the quadratic formula. So let's try it by factoring. So 6 should be in common in 24, which it is. Let's pull out a 6. So 6 goes into 24 4 times. So this would be a 4x squared. 6 goes into 72. Well, I am not quite sure. So I think to myself, 6 goes into 7 once with a remainder of 1, and 6 goes into 12 twice. So it goes in 12 times. So this is minus 12x plus, and then 6 times what is 54, which is 9. So I could see that this is use my rules of factoring. This is a trinomial, or this is a perfect square, and this is a perfect square. Or I can use that AC method, and we were just talking about that yesterday. So maybe let's go in and look at that AC method real quick. And so let's say we wanted to factor, let's do this on the side, this 4x squared minus 12x plus 9. So that AC method was, we look at that coefficient in front of the A, and in front of the square, which is our A value. Take that and multiply it to our constant, which is our C value. So A times C in our case is 4 times 9, which is 36. So we're looking for something that multiplies to give me 36 and adds the two numbers that would do that to give me the middle term, negative 12. Well, negative 6 times negative 6, right, is positive 36, and negative 6 plus negative 6 is negative 12. So those two numbers that we would use are negative 6 and negative 6. So the trick was to go back in and rewrite that middle term using those two numbers. And so if I do that, I have 4x squared. We have negative 12x is minus 6x. Minus 6x. So if I sum those, I get back the middle term. So it's okay to do that. Plus 9. Then the next trick was to go through, once you rewrote those, the middle term with those two numbers, is to go in and do factoring by grouping. So group the first two terms together, 4x squared minus 6x. We have a 2x in common that we can pull out. So if you pull a 2x out of the first two terms, what we're left with is a 2x minus 3. And now we're looking at the last two terms, negative 6x plus 9, and we think to ourselves, what does negative 6x and 9 have in common? Well, I know this, they have a 3 in common. The thing is, I want, when I pull out the number, I want the same thing in the parentheses, 2x minus 3. So in order to get that, I need to pull out a negative 3. So if I pull out a negative 3 from both of those terms, I get positive 2x and a minus 3. So if you've done this correctly, what's inside the parentheses is the same. You kind of think of this as one grouping here and one grouping here. And since they have the 2x minus 3 the same, we're just pulling out that whole grouping. We're factoring the 2x minus 3 out. And if we do that, from this piece, if we pull out this 2x minus 3, we're left with just the 2x. And then the second piece, if we pull out the parentheses 2x minus 3, we're just left with a minus 3. So 2x minus 3 times 2x minus 3 is the same thing, right, as 2x minus 3 quantity squared. So back over here, we showed we either have 6 times 2x minus 3 quantity squared. So we showed that they were equivalent doing it either method. So if that power had been higher than 3, then it just gets so tedious to have to expand it. And this is another place where using the chain rule would be a lot easier. So a lot of these derivatives, when you're asked to take a derivative, there's multiple ways you can approach it. You're trying to think about, okay, what's the easiest way that I can take this derivative that's not going to be so hard. I might not going to get as messy with all my algebra and expanding and adding like terms, etc. Okay, so this next example that we're trying to find the derivative, we actually cannot do without using this chain rule. Here we have f of x is equal to 8 times the square root, and what's underneath that radical is 4x squared plus 9. And we want to find the derivative. I just want to say right now, just so you don't do it, because notice that the square root of 4x squared, square root of 4 is 2, square root of x squared is x. And the square root of 9, right, is equal to 3. But if you have a sum underneath that radical, even though each piece is a square, we cannot, this is not the same thing as 2x plus 3. Okay, so we can't break it down like that. And so we need to use the chain rule. Recall that radicals, we could rewrite to have be an exponential form. So remember, square root of x could be written as x to the 1/2 power. And so we're going to want to rewrite this radical. We can do that now if we want. So f of x is equal to 8 times this 4x squared plus 9, all raised to the 1/2 power. So our inner function, let's say g of x, let's that be what's inside the parentheses, 4x squared plus 9. I call this function f of x, so maybe we can call our outer function h of x this time. So h of x, it's everything that doesn't have our g of x in it. And wherever we see g of x, it has to be just x. So I notice I have this 8 out here, so I need this 8, parentheses, to the 1/2. This inner piece is g of x, so I'm just replacing where g of x is with a single x. So this is our outer function. And we have our inner function. So I've been breaking it up as each piece and taking the derivative and going back and plugging it in, but we can kind of do this all at once. So let's kind of think about it. So if I took the derivative, it's the derivative of the outer. So we're going to take our power down front. Well, I have that 8 there. So I'm going to have 8 times my power. I'm just going to write it as 1/2 of the inner. Well, my inner function was just this 4x squared plus 9. But this 1/2 power, I have to subtract 1 times the derivative. So sometimes here, because we might just say that we're going to take the derivative of the inner, so d dx of 4x squared plus 9. And I'll show you why that can be helpful when you have multiple derivatives, where you maybe what's inside also needs the chain rule. Okay, so let's simplify this. 8 times 1/2 is 4. All times 4x squared plus 9. And 1/2 minus 1 is negative 1/2. And now as we're at it, let's just take the derivative of the inner piece. So times the derivative of 4x squared, which is bring our power down front times 4. So 2 times 4 is 8x. Subtract 1 from our power, it's just 1. Derivative of a constant is 0. So I can multiply my 8 times this 8x, because this 8x doesn't have an exponent other than 1. So 8 times 8x, this is 32x. And let's rewrite, because we have a negative exponent. Let's rewrite that. We can bring that all down to the denominator, right? And make that exponent positive by rules of exponents. So all over 4x squared plus 9 raised to the, now it's positive 1/2 power. Which we can rewrite in radical form, which is 32x all over the square root of 4x squared plus 9. So I just want to look at the chain rule in different notation. And so it says if y is a function of u, so y is equal to some f of u, our variables in terms of u, and u is a function of x, we say y, which is equal to f of u, oops, sorry. So let's go back over here. Say u is equal to g of x. Then we can say that y, which is equal to f of u, is equal to f of, but u is g of x, g of x. And the derivative, dy dx, this is equal to the derivative of y with respect to u, all times the derivative of u with respect to x. So dy dx equals dy du times du dx. So let's look at an example using it this way. So if f of x was equal to -7 all times parentheses 3x to the 4th plus 5 all raised to the -4 power. So pretty much the same thing, we're just kind of calling them different. So let u equal 3x to the 4th plus 5. Then I noticed that f of u, so instead of plugging in x, I'm going to plug in u here. My f of u is equal to this -7, parentheses. I see the u value here, so I'm going to replace it with u, all raised to the -4 power. Okay, so we want to look at dy du. And remember, this is y. So we need to find two separate pieces, dy du. So dy du, the derivative of y with respect to u. We're just using the general power rule. Bring our power down front. So we have our -7 times our power, -4, u, and then we're subtracting 1 from our power of -4. So -4 minus 1 is -5. Or dy du, cleaning it up, -7 times -4 is +28, u to the -5. And now we want to look at du dx. Well, this is our u, then the derivative of u with respect to x. So let's bring our power down front. 4 times 3 is 12. X, subtract 1 from our power, we get a cubed. Derivative of constant is 0. Oops. So putting it together, dy dx is equal to dy du, which we found to be 28u to the negative fifth, times du dx. Du dx. We found du dx to be this times 12x cubed. Okay, so the thing is that we wanted to find dy dx. We want this all to be in terms of x. So this is where here, we're going to go back in. We know that u is 3x to the fourth plus 5. So we can go in and plug in what u is right here. So this is equal to 28. I see a u there, so I'm replacing it with what it is, 3x to the fourth plus 5, all raised to the negative fifth power, times this 12x cubed. So I would probably clean it up by multiplying 28 times 12, which gives us 336. So we have 336 x cubed, all times 3x to the fourth plus 5 to the negative fifth. So that is using this other notation, dy dx equals dy du times du dx. But let's just go back and just do it one more time, but with the other notation. So if f of x again is this just negative 7, 3x to the fourth plus 5 raised to the negative 4 power. So the outer function taking the derivative of this outer function. So bring our power down front, negative 4 times negative 7. That gives us positive 28. Of the inside, 3x to the fourth plus 5, subtract 1 from our exponent. So negative 4 minus 5, minus 1 is negative 5. Times the derivative of the inside, d dx of the inside, 3x to the fourth plus 5. So a lot of times students forget that derivative of the inside, multiplying. And so sometimes just getting used to writing each time that I'm going to take the derivative of the inside, maybe you won't forget it. So we have 28, this 3x to the fourth plus 5, all raised to the negative fifth power. Taking the derivative of the inside, well, we found that above, but it's easy to do. 4 times 3 is 12. Subtract 1 from our power, so we have 12x cubed. Multiply 28 times 12, that's still 336x, and then we have an x cubed, 3x to the fourth plus 5 raised to the negative fifth, which is the exact same thing we got above. So to me, knowing that general power rule and doing it that way is a lot faster. Although when you have a complicated function, actually going the way above might be a little more neater and less room for mistake.